210 -1. We're recording. Okay, hi again. Welcome back to 234. Today we're going to review for exam number 1, which we take tomorrow in recitation. So make sure you go to your recitation tomorrow because the exam is there. Some things you should know about the exam. It's 50 minutes long. You get the whole recitation. You do not need to bring a calculator or a formula sheet. First, because you can't use a calculator. Second, because we're going to pass out formula sheets to you in class. So you'll be provided with a formula sheet. You do not need to bring one of your own. The only thing you need to have with you is a pencil and probably an eraser. Or if you're feeling particularly bold, you could also have a pen. But we would recommend a pencil because occasionally you do need to erase some things. So better if you can. Hey, stop. What else should I say about the exam and its format? It is just a little bit more than 4 questions, all free response. There aren't any multiple choice on the exam, so it's all just you take it and you go. Covers the first however many classes we've had so far. Again, that's more than 4, so that many. And the content on the exam is going to be mostly what we go over right now. So without much further ado, let's start the review. So the first question I've got prepared, and I may be bouncing around in order to cover all the questions I want to before we run out of time. But for this first one, we want to find the equation of a sphere in standard form that's centered at that point and has a radius of 5. Standard form is also the one that looks like it's center radius form. So it'll look just like this. I'm going to have x plus 1 squared plus y plus 4 squared plus z minus 4 squared all equal to 5 squared. Right, where that 1 is coming from that number, this plus 4 is the y value of our center, and then minus 4 is the z value of our center. So it looks basically just like it's a circle, but with the z squared term tacked on. So equation of a sphere, equation of a circle ought to look pretty similar to us. All right, and then the first real fun one we get to. So find a decomposition of the vector A into C and D, where C is parallel to an additional vector, B, and D is perpendicular to that vector. And I also want that decomposition to work out such that C plus D is equal to A. Or in other words, I want to find the yellow and the pink vector sketched out in that diagram. So I've got my particular vector of interest A. I want to project it onto B. And then I want to find the orthogonal projection of A onto D. Is effectively what this question's asking, just with some extra words. So I took the liberty of writing out the projection formula. It's right there. I believe you can just pull that right off of the formula sheet. So if you need that projection formula, you'll have it. Really hope I'm right about that. I'm sure someone will let me know if I'm not. Hopefully they'll let me know in time. But right, let's go ahead and put this stuff all together. I want to take the dot product of A with, let me just put it on screen. There we go. It is -3, 5, -5. And I want the dot product of it with B, which is 110, -2. All of that is over the magnitude of B squared. So that'll be 1 squared plus 10 squared plus -2 squared. And then I'm going to take that whole thing and just multiply it into b. 1, 10, -2. And I'll just come over here and highlight that part in blue because everything else is based on vector b. So all I've got to do now is resolve some of this math, which I don't think is going to look too bad in the end. -3 times 1 is -3 plus this will be 50 plus 10. If I just do my dot product right across the top, divide that thing by 1 plus 100 plus 4. And still multiply that into our b vector, 1, 10, -2. And finally, call this thing what, 57 over 105 times 1, 10, -2. And that's where I'd leave my answer for part, or for vector c at least. Let's come back here and write that in. C, it's that vector. Notice in the end, our parallel projection, when we're projecting A onto B, our result is a vector that goes in the same direction as B. Right? It's just some scalar multiple of B, which ought to make sense. Again, if we check back on the diagram, that yellow vector is just a piece of the gray vector. Hi. I do need to keep everything at the bottom under a square root. And I also forgot to write down that that thing was squared. All right, if we look back up to the formula, I've got the magnitude of b on the denominator twice. Yep. I think at least I hope I said that as I was writing it down. I just forgot to write the extra squared in there. Yeah. But yeah, if not for that second magnitude, yeah, I should have kept the whole denominator under square root. But this is only half of the problem. We wanted a decomposition into both A or C and D. So if I've got that A needs to be equal to the sum of its two decomposition vectors, C and D, that means that D, the new thing I want to find, should just be A minus C. Vector A minus that vector C. And at this point, I know all of that stuff, so I can just write it in. This looks like -3, 5, -5. That was vector A minus C, which is 57 over 105 times 1, 10, -2. And again, I would just leave my answer right here. I think that's going to be good enough. Particularly since we won't be asking you to multiply too many big numbers together. I think almost all of our multiplication and addition will be with single digit numbers. And we'll stay within like the integer set on the exam, since again, the calculator won't be there. So just leave your answer in terms of nice enough looking numbers, whether that's whole numbers or rational numbers. You don't need to advance your answer any beyond this form. If it were me, that's what I would do anyway. All right, so another one. What are we doing here? We want to evaluate the or the magnitude of a cross product. Given that the magnitude of A is 4, the magnitude of B is 2, and the angle between A and B is pi over 3 radians. So I've got one of the geometric formulas written down on the screen. That's our dot product geometric interpretation. But we wanted the one for the cross product. I'll go look at A cross B. Its magnitude is the magnitude of A times the magnitude of B times sine of theta. So mostly I've got the dot product example on here just to contrast the two. Because those two formulas do look very similar to each other. Whether I'm looking for the dot product, magnitude of the cross product. Again, pretty similar, except that the dot product is related to cosine of the angle between the vectors, whereas the cross product will be related to the sine of the angle between those vectors. But then all we've got to do is plug that stuff in. This is 4, that is 2. And then I need the sine of pi over 3, which if you recall back to your trigonometry class, sine of pi over 3 is root 3 over 2. And then I suppose I could simplify that a little bit, call it 4 square root 3. But I don't think we need to mess with that answer any further than that. Right, here is another fun one. What do we want this time? Find the area of triangle ABC, given that A, B, and C are the points listed right there. And in order to do that, we should find a few things. Ultimately, if I want the area of a triangle, I know that's going to be half the area of a parallelogram seen on screen. And I know I can get the area of the parallelogram by doing the same thing we did in the previous example, taking the magnitude of a cross product. In particular, the cross product I'm going to look at is AB cross AC. Right, if I look at those two vectors and take their cross product, or at least take the magnitude of their cross product, I should get the area of the parallelogram. And then if I just cut that in half, I'll get the area of the triangle. So, step 1, finding vectors A, B, and AC. So, AB should be B minus A, so -6 minus -3. And then I've got 3 minus 1 and -2 minus -2. Which I'll simplify to -3 to 0. Repeat that process to get a C, or the vector that goes from point A to point C. So I want C minus A. That looks like -5 minus -3, 1 minus 1, and -2 minus -2. In the end, -2, 0, 0. So hopefully that one's all right. Scroll down just a little bit so I can write down my next piece, which is finding the cross product of these two vectors. AB cross AC. Worry about taking its magnitude later. For now, I just want I, J, K with -3, 2, 0, and -2, 0, 0. Man, why does my handwriting look so bad today? -2. Maybe you guys can't tell the difference. That's fine. So I need to just calculate that cross product. So if we do that, I'm going to have 2 times 0 minus 0 times 0. Then 0 times -2 minus 0 times -3. And then finally, -3 times 0 minus -2 times 2, which becomes a +4. So in the end, 0, 0, 4 is what I got from that cross product. Don't hear any whispers out there, so probably I got that math all right. So for the last bit, I just need to figure out the area of that triangle, which, as stated at the beginning, it is half of the magnitude of this cross product, AB cross AC. Don't forget your vector hats. Put the other end of the magnitude on there. So this is going to be 1/2 of the square root of 0 plus 0 plus 4 squared, which is going to be 2. Right, that cross product has a magnitude of 4, and then half of 4 is 2. So these would be about the kind of numbers I would expect to see on the exam. Because again, we'll be aiming at stuff that you do not need a calculator to solve. So we'll keep all of the numbers relatively simple. We won't expect you to calculate anything outside of at least not outside of the rational set of numbers or rationals. Take all that back. We won't ask for much outside of multiplication of some one-digit numbers. And if you do have an answer that's outside the rationals, it'll be something like a pi or a square root of 3/2, something that comes from just the unit circle. So if you can do all of that, then I think that's going to be plenty for the exam. If you do need help with a calculation, if you're just completely panicking on the exam and your mind goes blank, you can probably ask your recitation instructor to help you out with some simple arithmetic. Don't think we'll consider that a breach of testing protocol or whatever. But again, expect relatively simple numbers on the exam. What else have we got? All right, I want to find a non-zero vector that is normal to the plane, this thing. So I really just want to pick out a normal vector for this plane equation. So I'm going to put it into a form that I recognize a little bit better. I'll call this thing z equals -5x plus 15 is equal to -16 plus 4y. Right, I'll just distribute those coefficients. And then I'm going to group all of my terms on one side. So how about the left side? This will be -5x minus 4y plus z. And then I've got 15 plus 16 is plus 31 equals 0. Because from here, I can pick out my normal vector. It should just be the coefficients on x, y, and z. So my normal vector, I'll call it n, is -5, -4, 1. Since I just need a normal vector, any scalar multiple of that vector, or any vector that is parallel to -5, -4, 1, will also solve the problem. This just seemed like the easiest one to get. But I think if you just moved all of your terms to the other side, you could have easily gotten 5, 4, -1. It's the other most common answer I would see in this problem. And we'll, of course, accept either one. All you need is a vector that is normal to the plane, not any specific one. All right, then the next one. Zoom out on this. I would say you could definitely expect to see a problem similar to this on the exam. Distance between a point and a plane is kind of a favorite of several of the people on the instruction team for Math 234. So be prepared for a distance from a point to a plane kind of problem. In particular, I think this one's looking for the distance between a line and a plane. But really, the distance between a line and a plane is going to be the same as the distance between a point and a plane. All we're going to do is, I suppose, verify that our line is actually parallel to the plane. If our line isn't parallel to the plane, the distance is going to be 0 because that line and that plane would intersect somewhere. But if they are parallel, there's a fixed distance between them, and the distance between the point and or between the plane and the line is really just the same as the distance between any point on the line and the plane. So that's what we're going to do. Pick some point out here on the plane. I'm going to call it Q. Pick any point that's on the plane. I'm going to call it P. And go look at the distance or the vector that connects those 2 points. Right. That vector will be PQ. Now, I don't care about any point. I don't care about any specific point in the plane. I don't care about any specific point on the line. I just need the vector that contains the 2 of them. And then you'll probably notice that that means that vector, PQ, doesn't actually give the shortest distance between the line and the plane. But that's okay, because all I need to do is take that vector, whatever vector it might be, and project it onto the normal vector, which will get me the shortest distance between the 2. So let's call that vector C. Which means I'm going back to my projection formula. So if I'm looking for a distance between a point and a plane, I'm really looking at calculating some sort of a projection. Or rather specifically, I just need the component of that projection. So what do we want to do here? Probably start picking out some of these elements. If I come back up to my point Q, I think that's the easiest element to pick out. Just set t equal to 0. And you should get a point that's on the line. In particular, we have -1, -2, -1. -2, nope, -1, -2, -1. I'll also need a normal vector, which I can pull just out of my plane equation. N can be the vector 1, 3, 2. As again, just grab the coefficients out of x, y, and z, just like the previous problem. And I need a point that's on this plane. Any point will do. So I think the easiest looking point is going to be -23, 0, 0. So I'm kind of just pulling that point out of nowhere. There are infinity squared points that are on the plane. So I can kind of choose whichever one I want. If I look back at the equation of my plane, x plus 3y plus 2z equals -23. I've got one equation with 3 variables, so I have 2 free choices. And it looked to me like the easiest couple of free choices would be to set y and z both equal to 0, and then just figure out what x has to be if y and z are 0. 23 or -23, 0, 0 is definitely not the only point that I could use to solve the problem. Just seemed like the easiest one to pick out. I didn't have to divide a 2 or a 3 over into 23, which is a prime number. So I'm not going to have to deal with a fraction. It's kind of why I chose that point. Again, there are an infinite number of points that you could pick. That's just the one that stood out to me. Now, so maybe writing down how I got that. I set y equal to 0 and z equal to 0. Just because it looked like the math would be easier. So now I've just got to write down all of this stuff. I need vector PQ. So PQ. Let's put a blue hat on it. It is the vector -1 minus -23. So plus 23. And then -2 minus 0, -1 minus 0, giving me a result of 22, -2, -1. And then my real goal here was to find the magnitude of C, which is really just the component of PQ projected onto my normal vector, which was N. And that component is going to be the dot product of 22, -2, -1 with my normal vector, which was 1, 3, 2. And since all I need is the component, I'll divide that by the magnitude of the normal vector, 1 squared plus 3 squared plus 2 squared. Because in the end, I don't actually care about the normal vector's magnitude, right? I don't want the magnitude of the normal vector to impact the distance between my two pieces. So I divide the magnitude of that normal vector away so that the only magnitude that remains is the magnitude of PQ, sort of. So if you kind of stretch it a little bit, it makes sense, I promise. One last thing I should add on here is probably an absolute value around this dot product. Since we won't consider a distance to be negative in this case, we'll just look at the distance being an absolute value. It doesn't matter if I'm going to be above or below the plane. If I'm 4 away, it doesn't matter if I'm 4 up or 4 down, my distance is 4. But moving on. I should calculate O dot product here. It looks like something. 22 times 1, 22 times 1, plus -2 times 3, so -6, and -1 times -2 is a -2. All of that is over the square root of 9 plus 1 plus 4, which is 14. So I think this looks like 14 divided by the square root of 14, and if you rationalize that number, I think you just get square root 14. But I'd take either answer. If you left it as 14 over root 14, that'd be fine. Ooh, come on. Technology save me. There we go. Get a box. Just to highlight a second way that you could have solved this problem, I generally prefer to think of the component of the projection because I can always work my way there from remembering just a couple of pieces. It's less, let's call it memory power that I've got to bring into the problem. So I can just kind of sketch my way there. But there is another formula. I don't believe this one's on the formula sheet though, so you would just have to remember this one. But there is a formula for the distance between a plane and a point, and it's given right there. I think we went over it in class. So you can use that if you want to. As long as you arrive at a correct answer, we're not going to be picky about the particular method. We'll take that back. Of course, we'll be picky about the method. As long as you use a correct method, we won't be picky. So you could, of course, arrive at the correct answer with a bad method, and well, we'll probably catch that. So use a correct method, I guess. But again, I digress. Let's go to some other things. Everybody's favorite WebWorks set. Identifying quadratic surfaces. So, if you get a problem on the exam where you have to identify a quadratic surface, my best and first advice to you is to ignore all of the numbers. So all of these over 4s, I'm just going to pretend they're not there. They're not going to be helpful to us. I'm just going to get rid of them. I can come back and worry about the numbers at the end if I need to, but all I'm trying to do is identify the surface. The numbers are just gonna make it worse for you. So instead, I just like to look at x, y, z, and whatever constant value I might have. That constant value will be either 0, 1, or -1. And then match up a shape from there. And then if I need to scale my shape back out to what it really looks like, I'll just add the numbers in at that stage. Most of the time, don't need to worry about it though. So let's take a look at what we've got. Yeah, it is. Mhm. At least it could be. It's in the set of things that we're testing on. I don't remember exactly every single problem that's on there, but I think there's one that's like, quick, identify a couple of surfaces, I think. Oh, that was excluding the introduction to cylindrical and spherical coordinates, which is Friday's lesson. The reason that's in the announcement is because in some of the literature, that section is snuck into chapter 13. So saying it's in, when I say we're quizzing or testing on chapter 13, it's not on this very last section of chapter 13. Which, ought to make sense because we haven't actually taught the lesson on that yet. This part could be on there. Yes. Hi.
Will we be given any of that on the equation sheet or?
I don't believe so. If you're talking about like the thing from the textbook on the side, I don't think that's on the formula sheet. Don't forget that you can see the formula sheet ahead of time. It's linked in the announcement right on the front page D2L. Our front page D2L. But getting back to identifying these surfaces, let me highlight one of them to work out. Let's go with this guy right here. I've got x squared minus y squared minus z squared equals 1. And I'm going to try to figure out what kind of shape that thing is. So my preferred method, once I've gotten rid of all of the numbers, is to aggregate my terms so that I have a majority of positive terms, at least for the variables. So I would identify this thing from this equation. Negative x squared plus y squared plus z squared equals -1. I basically just multiplying my entire equation by -1 so that I have it in a way that makes sense to me. Because I know if I've got 3 square terms, it's not one of the parabolic shapes, so I can exclude those. My 3 variable terms do not all have the same sign, so it's not a sphere or an ellipsoid, which means it's one of the other options. It's either a cone or it's one of my 2 hyperboloids. So that's my sort of sorting algorithm. It's a cone if that thing is equal to 0. It'll be a hyperboloid of 1 sheet if it's equal to a positive number, and a hyperboloid of 2 sheets if it's equal to a negative number. So since this thing's equal to a negative over here, that's going to be 2 sheets. 2 sheets. So identify that shape as a hyperboloid. Yeah. Hyperboloid. Let's just go with that. 2 sheets. Where, the 2 is the interesting part there. So that'd be my method for figuring this one out. I know that this hyperboloid is going to be expanding along the x-axis because that's the only negative variable, meaning that there's the blank space in that hyperboloid of 2 sheets. If I go pull that over, that blank space right here, I have my 2 dishes are going to be expanding along the x-axis and back along the negative x-axis. So it's the YZ plane that runs through the middle of my shape. That'd be, again, my method for solving that problem. To fill in the rest of these, I think the ellipsoids are usually pretty easy to spot. Just put all of your square terms on one side. If they all have the same sign, that's an ellipsoid. Think like a circle or a sphere. I've got a cone for the third shape, also relatively easy to spot because the constant term is 0. But I have a bunch of square terms. The fifth one, another pretty easy to spot ellipsoid. In fact, that one is just the unit sphere. But unit sphere is just within the category of ellipsoids. And I have another cone at the end as well. I skipped the first one. But that one's going to be another hyperboloid, but this one's only of 1 sheet. All right, I'll see if I move my y squared over to the left. One of my 3 square terms has a different sign from the other 2, so it's one of the hyperboloids or a cone. And this time it's equal to a positive number, making it 1 sheet high.
But it doesn't matter which term is negative in those.
That is correct. It does not matter which term is negative. In fact, the negative term will just determine which axis these things expand along. Right? If I look at my right column, each of these sketches are for a negative z-squared term. So they all expand along the z-axis or are formed around the z-axis. So if I just have a different negative term, it'll just switch that to expand along a different axis. Ooh, and right. With our remaining time, let's see how many of these other problems we can hit. So yeah, we've got some vector functions. So what would we like to do here? Hang on one moment. All right, well, we'll get through as much of them as we can, I suppose. All right, going over this first one. So given r prime is that derivative vector, and r1 is 9, 10, 12, find the original function, so solve the initial value problem. So when we start with just r of t is equal to the vector that is just the integral of each of these pieces. I need the integral of 10t plus 4 dt. Let's not forget our dt's, then it'll be a bad luck. The integral of 5 dt and the integral of 12 square root t dt. So I would integrate that stuff. I would get 5t squared plus 4t. And then the other things that I get, I'm going to skip those steps in the interest of time. Just solving out the x component. I also have a plus c vector in the end. The rest of the initial value problem is just about finding that c. So I know that at r of 1, 5t squared, there we go. 5 times 1 squared plus 4 times 1 plus c1 should be equal to the x value in my single point that I was given. In this particular case, it's 9. So then I will solve for c1. This looks like 9 plus c1 equals 9. So c1 is 0. And that'll be my x component. Repeat that process 2 more times, once for the y component, once for the z component, and that problem's solved. So again, in the interest of time, I'll skip over that for now. But if you check in my notes, look for the exam reviews tab, you can see all of these problems worked out completely right there. So exam reviews over on the left, just like for exam 1 review, you can find the full solution set there. Stop that. Okay. On to the next one that we're definitely going to have time for. At what points does the curve RT intersect the paraboloid z equals x squared plus 5y squared? Well, I just want to plug that point or plug that curve into the paraboloid. So I'll have something like 5t minus t squared is equal to 7t squared plus 0 squared. All right, if I just notice over on that curve, my j term is missing, which means the y component is 0. So when I plug it in there, I get 0. I suppose technically this should have been a 5 times 0 squared. But either way, it's still going to work out to 0. So this thing looks like 5t minus t squared equal to 49t squared, which gives me the equation 0 equals 50t squared minus 5t. I just move those over to one side. So 0 is 5t times, that looks like 10t minus 1. If I factor those out, giving me two results, t equals 0 and t equals 1/10. So then I'll go find r of 0 and r of 1/10. Right, I can just plug those back in. And I'll leave that for later, since with our last 5 minutes are a couple other problems I really wanted to get to. In particular, parameterizations. This is another one that I'm sure you'll want to see for the exam. So we'll work this one out in its entirety. So I'm going to have a curve of intersection between a cylinder and an unknown surface. Z equals 2xy, and by unknown, I just mean we're not going to classify what it is. We want to figure out what a good parameterization of that curve is going to be. So, first thing I notice here, it's equal, I have x squared plus y squared equal to 81, and in particular, that is a constant. So I am immediately thinking that sine and cosine are going to be a good choice for this parameterization. So I'll use x equals 9 cosine t and y equals 9 sine t, since I have x squared plus y squared. I think we saw in class that if it were like x squared plus z squared, it would just be x is cosine and then z is sine, something like that. Whatever two terms show up in that equation that looks an awful lot like a circle should be sine and cosine. Our radius is 9, since that's the square root of 81, so I dropped that in there. Now, if we had something like x squared plus y squared equals 81z, I'm probably going to be thinking about something else. I don't necessarily think that sine and cosine are a good choice here. Because I want it specifically to be when I've got it equal to a constant value. If I've got an extra variable over on that other side, that tends to break the sine and cosine parameterization. Not always, but sort of as a rule of thumb, I look away from sine and cosine if I've got two square terms added that it's equal to something that's not constant. But once I get sine and cosine, from there, I can just get z by plugging them in. So this will be 2 times 9 cosine t times 9 sine t. And if I really wanted to simplify that, I could call it 81 times the sine of 2t, since that looks an awful lot like the formula for the sine double angle. The sine double angle formula. There we go. Again, though, that won't be necessary. You can just leave it. You can leave it just in that top example. That'll be good enough. So one more shot at this. If I've got another set of things, where again I've got x squared and z squared added together, but this time it's equal to y. Now I'm not thinking that this is a great idea, or this is not a great problem to use sine and cosine for my parameterization. So I will instead try something different. And I am going to jump to z equal to t. Reason I'm thinking that, I've got x equals z squared. I really don't want to have to take the square root of z in order to figure out, or I don't want to take the square root of both sides to figure out what z should be. So that'll introduce a plus or minus, which isn't great. But if I instead let z be equal to t, then x can just be t squared. I get two very nice parameters, or two very nice equations right away. If z is t, then x can be t squared. And then that leaves us with y being equal to 13 times t to the fourth. T to the fourth. There we go. X squared squared, or t squared squared. Plus 4t squared. And just like that, I have a really nice parameterization. And all right, ran out of time to cover arc length. But let me go just highlight a couple of other of the worked out problems that are on here. This one I think is a good one to look at. We want to find the point of intersection between two curves, and then also the angle of intersection between those two curves. If I want to find their point of intersection, and I'm just going to talk about my process here. Set their component functions equal to each other, x and y and t. Start substituting to figure out what s and t are. And then to find the angle between them, I want the angle between their tangent vectors. So I'll take derivatives, plug in the s and t values that I found, and then plug it into the angle formula. I'm going to use the dot product because I think it's easier. Once again, as you won't have a calculator, you should leave your answer just as it is, not some arc cosine bit. Cool. All right. And then we are at the end of class time. So I'll pause here for a minute for anybody that's got to go. For anybody that wants to stick around, I'm going to work out that last arc length problem. But again, totally optional. If you've got to be somewhere else, have fun getting to your next thing. Good luck on the exam tomorrow. I believe in you. But for the last one, just going to work out this arc length problem real quick. So the arc length, I believe this formula is given on the exam. I need the integral from A to B. From A, let's turn that off, to B. So the magnitude of R prime of T dt. And hang on 1 second. All right, and we're back. Sorry to whoever's coming in for the next class. You're gonna learn some Calc 3 real quick. It's gonna be fun, I promise. So we were in the middle of figuring out the arc length of this curve between -1 and 4. So we want to find the derivative vector, which looks to me like it's going to be 2 cosine 2t and -2 sine 2t. So we want to integrate the magnitude of that vector from -1 to 4. So don't forget that part right there. So that magnitude is going to look like what? 4 plus 4 cosine squared of 2t plus 4 sine squared of 2t dt. Don't forget that, a negative gets squared away when we square those two bits. After that, what am I looking at here? I've got a trig identity in the middle. Sine squared plus cosine squared is equal to 1. So this looks like the integral of -1 to 4, the square root of 4 plus 4 times 1 dt. And then that's got a pretty nice integral. That's just going to integrate to the square root of 8 times t. Evaluate that from -1 to 4. And that's going to be 5 times the square root of 8. Cool. And then if we really wanted to, I could pull another number out of there, call it 10 square root 2. But I don't think that's strictly necessary. Okay, and then that's the end of my review for the first exam. So I'm going to stop my video here. Okay, bye, 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 bye.